Hello, I am Mohammed Mati. I am going to be talking about efficient execution of dynamic programming algorithms on Apache Spark. This work was done with my co-authors at Stony Brook University, Colorado State University, and University at Buffalo. Today, supercomputers consist of a network of distributed memory hybrid compute nodes, each having multi-core CPUs and many core GPUs. Inside each supercomputer, different types of parallelism exist: distributed memory parallelism and shared memory parallelism, including task level and data level parallelism. Inside a supercomputer, there are usually different types of compute nodes. For example, in the Comet supercomputer, we have Intel Haswell standard compute nodes, large memory Haswell nodes, as well as different types of NVIDIA GPU nodes. Such heterogeneous architecture is different from one supercomputer to another one. Here in this figure, as of June 2020, we can see different architectures in different supercomputers, such as Fugaku, Summit, Sierra, and so on. More interestingly, in one supercomputer, the architecture is rapidly upgraded. For example, the supercomputer Lone Star got upgraded several times in 2004, 2006, 2007, 2011, and 2015. As a result, efficient algorithm for such heterogeneous and constantly evolving supercomputers must exploit various types of parallelism, must exploit data locality at various levels of computation, and must have performance portability across different nodes in a supercomputer, across different supercomputers, and along the time dimension. There are two important features of compute clouds and clusters. The first is the capability to scale out by adding more compute resources. This is great as long as the computation or the algorithm itself can scale out, which means it should be well decomposable. Also, there is an important trade-off between communication cost, parallelism, and memory requirement, which means that the computation or the algorithm should be tunable. Our claim is parametric multi-way recursive divide and conquer dynamic programming algorithms, or in short, parametric R-way RDPs, are efficient solutions for modern supercomputers, compute clouds, and clusters, because they do have the two important requirements, well-decomposability and tunability. In order to show our claim, we designed and implemented these algorithms on Apache Spark and provided experimental results illustrating the performance and portability of the programs. In the rest of my presentation, I will have a quick introduction to Apache Spark and then dynamic programming algorithms. Then I will talk about recursive divide and conquer formulation of DP algorithms by summarizing standard two-way Rdp algorithms. Then I will explain why we actually need to have more general solution, which is parametric R-way Rdp algorithms. I will summarize the two design methodologies to obtain these algorithms. The first one is called inline and optimize, and the second one is multi-way autogen, which is a framework based on polyhedral compiler technology. Later, I will talk about how we can map these algorithms to Apache Spark, and finally, I will present the experimental results. Apache Spark is a high-performance, scalable, general-purpose distributed computing system. Through easy-to-use APIs and the simple abstractions, one can do rapid program development and test the program on small datasets. However, it is very straightforward to deploy the program on the cluster or cloud to operate on big data without any significant modifications. There are three important concepts in Apache Spark. The first one is resilient distributed dataset, or in short RDD. RDD is a core data abstraction representing lazily evaluated distributed collections of data. RDDs are further divided into partitions. Apache Spark reduces I/O in repeated computations by keeping the partitions in memory as much as possible. As a result, it is usually faster than Hadoop's MapReduce. The second important concept is called transformation, which is a computation that takes input RDDs and generates output RDD. There are two types of transformations: transformations with narrow dependencies and transformations with wide dependencies. In transformation with narrow dependencies, an output RDD is dependent on only a single input RDD, and as a result, there is no data shuffle. So communication among compute nodes is not needed. However, in transformation with wide dependencies, an output RDD is dependent on more than one input RDD, and as a result, data shuffle or communication is usually needed. So these transformations are very expensive. The third important concept is called action, which is a computation that takes input RDDs and generates final result. The difference between transformation and action is transformations are lazily evaluated, which means that they get computed only when an action is triggered. Action triggers the scheduler to build a directed acyclic graph, or in short DAG, whose edges are determined by the dependencies between the transformations. Spark uses this DAG to define a series of steps called execution plan to produce the final result. Lazy evaluation helps Spark to optimize the execution plan by grouping or fusing together the transformation to avoid doing multiple passes through the underlying data, which leads to improved efficiency. Dynamic programming algorithms are everywhere. They have applications in bioinformatics, graph problems, compilers, NLP, and so on. DP algorithm solves a problem by recursively breaking it into smaller subproblems. It solves each unique subproblem exactly once, and it stores the solutions to subproblems in a table for reuse. In every DP solution, we have a recurrence relation which specifies how and in which order the subproblems must be solved. A typical DP algorithm uses nested for loops, but it has been shown that such loop-based algorithm doesn't have good temporal locality in its data access pattern. Here's an example of a loop-based DP algorithm, Gaussian elimination without pivoting. We can see that there are for loops like for k, for I, for j, and ultimately there's a statement updating some cells inside the DP table. The figure also shows that the red cell xi and j is dependent on all the green cells above, to its left, and on the diagonal. Because of poor temporal locality exists in loop-based algorithms, several researchers have introduced classic two-way Rdp algorithms. Here, as an example, I am showing the two-way Rdp algorithm for Gaussian elimination without pivoting problem. It starts by recursively calling itself to update top-left submetrics x1 and 1. Then it calls two other recursive functions b and c to update submatrices x1 and 2 and x2 and 1 in parallel. Then it calls another recursive function d to partially update submetrics x2 and 2. And finally, it recursively calls itself to complete the update in submetrics x2 and 2. In all these recursive functions, if problem size is small enough, instead of recursive solution, base case solution is executed, which is a loop-based implementation. Classic two-way Rdp algorithms have several limitations. In GPUs, which we have limited support for recursion, it is not possible to apply these algorithms directly. In distributed memory supercomputers, it is not straightforward to execute them on such clusters. Additionally, these algorithms do work decomposition recursively with low precision, often matching the required computation sizes only within a constant factor. As a result, a more generalized solution was introduced, which is parametric multi-way Rdp algorithms. Before getting into the details of design methodologies in order to obtain multi-way Rdp algorithms, let's look at an example. Here at the top, I have a standard two-way Rdp algorithm for Gaussian elimination problem, which I described in the previous slides. But here at the bottom, I have four-way recursive divide and conquer algorithm for the same problem. As we can see in this four-way recursive divide and conquer, I divide each dimension of the DP table into 4, and then there are a bunch of several function calls happening in parallel in each stage. Now, let's look at the first design methodology on how to obtain this algorithm. First, we use autogen or Bellmania to obtain the standard two-way Rdp functions for the given DP problem. Then, in a semi-automatic manner, we apply the following two steps repeatedly to derive the multi-way Rdp algorithm from the corresponding two-way Rdp1. The first step is to inline each recursive function call by one level, and the second step is to remove unnecessary coarse-grained dependencies. We repeat these two steps until we find the pattern and come up with the compact representation of the algorithm. Let's look at an example. We use autogen or Bellmania in order to obtain the two-way recursive divide and conquer specification for function A, similarly for function B, C, D. And then what we do is, as the first step, we inline the two-way Rdp. So what does it mean is, rather than calling the function, we replace it by the specification of itself. Similarly, we do the same for function B and function C. Now, we can see that rather than these coarse-grained function calls, we have finer-grained function calls, or these subfunctions. But due to the coarse-grained barrier between these coarse-grained function calls, none of these subfunction calls can happen in earlier stages. Although it is due to the data dependencies, they can happen. So in this state, we remove these unnecessary coarse-grained dependencies among the subtasks, and move the subfunction calls to the earliest stage that they can execute without violating the data dependency. After applying inline and optimized steps several times, by observing function calls, we can come up with a pattern. For example here, for function A, we see that it first calls itself on top leftmost submetrics x1 and 1. Then in the second stage, we have a bunch of function calls B and C executing in parallel in the first row and first column. And then we have a bunch of D function calls executing on the rest of the submatrices. And then in a repeated manner, we have A function call executing submetrics x2 and 2, then B and C function calls, and again a bunch of D function calls, and so on. This reveals the pattern, and we can come up with a compact representation of the algorithm for each of the recursive functions. The first design methodology that we discussed so far is semi-automatic, and it can be error-prone. As a result, the new design methodology was introduced, which can systematically drive the same algorithms, but using polyhedral compiler transformations such as monoparametric tiling, indexed splitting, dependence analysis for parallelization. The input to such design methodology or the framework is a polyhedral iterative DP or IDP program, which is fully tileable. It means that all the loops in the program carry only forward dependencies, and the memory access functions are affine functions of loop variables. Let's look at the high-level algorithm that the framework or this design methodology uses. In the first step, it applies monoparametric tiling to all the dimensions of the input program. Then it converts the tile program to a recursive one. And then, in order to come up with a more efficient recursive solution, it applies indexed splitting based on the criteria of overlapping or disjointness of output tiles with the input tiles. And then for the new cases obtained in the step 3, it defines a new serial function, it calls that new function, and then it processes it the same way. Now let's focus how we implement these algorithms in Apache Spark framework. If we take a look at these recursive algorithms, we see that there's a general iterative pattern of recursive function call exists in all of them. So this pattern indicates how to map these recursive function calls to Apache Spark framework. So what we do is, we always start recursive solution with function A. So we design the top level Spark program to execute the same sequence of recursive function calls A, B, C, and then D as kernels by Spark executor in different stages. So the kernels itself can be iterative or recursive. It is also worth mentioning that the underlying DP table is a pair RDD mapping from a 2D tile coordinate I and J to the underlying block of the data. Now, considering the communication among the kernels due to data dependencies among them, we can have two different Spark implementations which were originally introduced in ICPP 2019 paper. So the first one is called in-memory implementation, which in this implementation, after updating the block or the tile, each kernel is responsible to generate multiple copies of itself or the block to be used by the kernels in the next stage of the iteration. For example, we know that in Gaussian Elimination algorithm, this block is being used by all other kernels B, C, and D. So kernel A is responsible to update it as well as making such copies. So obviously, because of this multiple copies and data communication, we might have a very poor performance in such some benchmarks. The second implementation is called collect broadcast, which alleviates this costly data shuffle by using Spark action called collect, which brings the blocks to the Spark's driver node, and the driver node is responsible to distribute the blocks to the consumer executor through the shared persistent storage. So somehow we are trading off this costly data shuffle with storage. And obviously kernels, they don't need to make any copy of the updated tile anymore. Now let's look at the benchmarks that we targeted in this paper. Actually, the two benchmarks that we have experimented, Floyd-Warshall all-pair shortest path and also Gaussian elimination, they're actually a special case of this GEP form, which is a more general case that by changing the if condition in line 4 and the function f, we actually can get either of them. Now let's talk about the experimental setup. Actually, we used two clusters, Skylake and the Planix, both located at the Center for Computational Research at University at Buffalo. So cluster 1 had 16 compute nodes with a 216-core Intel Skylake processor with this information about its memory hierarchy and 1 terabyte of SSD drive. The second cluster also had 16 compute nodes, also dual 10-core Intel as well as this information about the memory hierarchy, but it had also a spinning hard drive. So there are some implementation details. We use Spark version 2.2, PySpark, and Python. The iterative kernels were implemented in Python and a Numba Jet compiler. So the iterative kernels were also offloaded to bare metal through NumPy and SciPy, but the recursive kernels were implemented in C, C++, and OpenMP, and they were compiled by GCC 7.3 with these flags OFAS and architecture to be native. Alright, for distributed memory parallelism, we solely relied on the capabilities of the Apache Spark, but for shared memory parallelism, we configured the Spark to run one executor per compute node. We set the total number of RDD partitions 2 times the total number of cores, and for recursive kernels, we use OpenMP for the task parallelism. So there's one more parameter to tune, OMP num thread. So for shared memory parallelism, we had 2 parameters to check different combinations of them. Executor cores, which determines the total number of logical tasks running in parallel inside one executor, and the parameters set in Spark, and OMP num thread, which is an OpenMP parameter. So the great observations that we had was if we set executor core to a specific value, by increasing OMP num threads, we could get better performance up to some point, but after some points, increasing the total, the OMP num threads could degrade the performance drastically, perhaps because of the thread oversubscription. So as a result, what we did was we set the executor cores to the total number of physical cores in a node, 32, and we executed the benchmarks with different values of OMP num threads and reported the best. Okay, in this slide, we are comparing different implementations with different kernels. For problem size of 32K by 32K and 16 compute nodes, we found the following interesting observations. First, for Floyd-Warshall all-page shortest path, in-memory implementations outperformed the collect broadcast implementations. However, in Gaussian elimination, collect broadcast implementations outperformed the in-memory implementations. As in Gaussian elimination, due to the data dependencies among the kernels, we had much higher communication costs in in-memory implementation. The second observation is in Floyd-Warshall, we had 2 times faster execution using recursive kernels, and in GE, we had 5 times faster execution using recursive kernels instead of iterative kernels. And the third observation is for small blocks, say 512, since the blocks fit into the L2 cache, performance of iterative kernels and recursive kernels were almost similar. However, for large block sizes, say for example 2K, we can see that the recursive kernels significantly outperform the iterative kernels. Here, finally, we are comparing the performance of benchmarks in 2 different clusters, and the most important observation we have here is if the algorithmic and system parameters, such as block size, kernel type, are chosen independent of system configuration, the resulting execution can be very inefficient. For example, considering the in-memory execution for block size 1K with recursive 4-way kernels, we can see that in the first cluster, it runs almost the fastest. However, in the second cluster, it runs 3.3 times slower than the best running time in this cluster. Great. As a conclusion, in this presentation, we introduced parametric RDPs as efficient solutions for modern supercomputers, compute clouds, and clusters because they have 2 important requirements, well-decomposability and tunability. We explained the design methodologies on how to obtain these algorithms and provided experimental results illustrating the performance of the programs. Future work includes designing and implementing Spark programs using parametric recursive divide and conquer approach beyond dynamic programming algorithms. And the second one is, for this paper, we have used the Spark's default partitioner, and hence we would like to design efficient customized partitioners as we know the data dependencies among the kernels. Thanks a lot for viewing this presentation, and we are looking forward to hearing great questions from you.